Okay, so today we're going to finish off the lecture on the final chapter, which is actually the fifth chapter, but somehow for this semester I introduced chapter 6 earlier than chapter 5. Okay, so internal combustion engine is, as described yesterday, is related to the manipulation of the mixtures of fuel and air. And then for yesterday, you already listened to the how we can differentiate between different types of internal combustion engines. And usually in, let me record this first. Okay. Usually the kind of assessment that you're going to face will involve as at the lowest kind of assessment will be, for example, you'll be requested to differentiate between spark ignition and also compression ignition engines. And then you need to sketch the different cycles for each of those. And then you need to explain what are the reference cycles. Okay. As for yesterday, we already saw that for the spark ignitions, we use the Otto cycle as the reference ideal cycle. Okay. Similarly, as for any other devices under the thermodynamics tool under this BDA 30403, so we always have what we call the stop the jolting. In thermodynamics too, we always have the ideal cycles or the ideal condition that we want to benchmark, and then we have the actual engineering devices that we always push the system to achieve. Okay, so right, so let's continue from yesterday. Yesterday we talked about the air standard cycle and then how we use the air standard cycle as the assumptions, and then we gone through the Otto cycle. Oops. Okay, so usually we define the cycle for internal combustion engines using the PV sketches. Okay, so for the Otto cycle, as you can see here, the distinct features of the cycle is that we have event what we call happening at the same volumes, because that is where the position of the piston will be at the bottom of the center or the top of the center. So when the piston is at the top of the center, which it means that the volume inside the cylinder is at the lowest amount. So we call it the V min, and then it's where you're going to compress the fuel and mixtures, and then it's the position where the piston will be before the initial combustion is happening. Okay, so for the spark ignitions, we have the spark plug to create the ignition to ignite the mixtures of fuel and air, and then everything is happening at the same volume. Okay, where you have the compression and then you have the ignitions, and then after that you have the expansion process. So if you look at the Otto cycle, you have the 3-4 the path is from state number 3 to state number 4. So you have the expansion process, and then from the expansion process you arrive at the maximum volume, so it's called Vmax. And then at the same time, it's where when the piston start to moving upwards again, it's where you start to remove or take away the resulting combustion byproduct, the exhaust gas from the chamber. The piston will move outwards and push out the exhaust gas outside the chamber, escaping through the exhaust valve. Okay. And then for the Otto cycle, we can define it as the isotropic compression, the constant volume heat addition. Okay, because for Otto cycle, we represent based on the air standard assumptions, we represent the call it the spark ignition process as the heat addition process, which is happening at constant volume conditions. So it's happening at between 2 and 3. Okay, in the Otto cycle, the working fluid is alternately expanded and compressed in pistons in the device. So we can use the we call it when we want to derive the equations, we use the assumption for the closed system. Okay, so this is what we went through yesterday. Usually, when you do the sketch for Otto cycle, you can it's okay to use the PV diagram. Okay, but if you want to provide both TS and PV, will be much better because the PV diagram will give out the variation of pressure with respect to the difference of volume, and the TS diagram will indicate how the temperature is changing and how it affect the entropy. And the good thing of having the TS sketch is that you can show the isentropic process and then how it relates to the position of the piston. Sometimes how it can affect the value of pressure. Okay. So I'm expecting students will be able to carry out a basic sketch, a PV or TS diagram, preferably the PV diagram. Okay, so the distinct features again, I repeat here, is the event is happening at the same volume from 4 to 1 and from 2 to 3. Okay, and then using the air standard assumption, can then work out the amount of heat that is being supplied during the compression process, as represented by the Q in during the top dead center positions. Okay. Then the amount of heat supply is equal to the change in the internal energy. Okay, because this is based on the specific flow energy equation. This is what's happening. The only changes that is experiencing by the compressed mixtures is the amount of internal energy. And then due to the spark ignition, it create the explosion, and then you have increase in temperature. So that's why you are using the specific heat at constant volume. Okay, when you want to convert the Q in, or you want to define the Q in, is based on the specific and constant volume, and then that's why you need to use the different temperature to calculate the amount of heat supply. Okay, so delta U is equal to CV multiplied by delta T. Okay, and then the same with the heat, the amount of heat rejected. Okay. The amount of heat rejected is also depends on the specific heat at constant volume, because the why we use the CV, because that's where the event is happening. Okay, at constant volume is where the mixtures is receiving the Q in, and it's where the mixture is also releasing the Q out. Okay, and then as usual, we then use the terminology for the polytropic process. Polytropic process is when you have the changes in the volume with respect to the pressure, and it's not a linear process. We call it a polytropic process, which is depend on the power of the for the equation. For in this example, we know that the ratio between the temperature and the ratio between the volume are related, and then among the key parameter is the value of K. Okay. So from where you need to find the K is you can obtain the value of K from the table, but you need to select the correct temperatures or to select the call it the what will be the suitable temperature range for the value of K. Okay, and then after that you calculate the efficiencies, and efficiency is calculated based on the same definitions, which is the amount of work produced, the net amount of work produced divided by the amount of heat supply into the system, and then we expand into Q out and Q in, in terms of Q out and Q in, and then from the Q out, we then refer back to the CV delta T, and then we expand again. So at the end, we have the efficiencies, which is defined based on the parameters of temperature. Okay, and then if you replace the temperature terms with this equation here, in relation to the ratio of volume, you can then rearrange in terms of K, and then you end up having this expression, okay, where the auto efficiencies is equal to 1 minus the value of 1 divided by R to the power K minus 1, using the cold air standard assumptions. So what is R? R is the compression ratio, which is the ratio between the maximum volume divided by the minimum volume. A note to the students: when you are using this equation to do some calculation, please remember that the temperature must be in Kelvin. Okay, the temperature when you do this calculation, especially for call it internal combustion engine, or maybe for throughout the chapters in thermodynamics too, temperatures when you do the calculation must be in Kelvin. So if you given the incoming temperature as 30 degrees Celsius, so you need to add up with the 273, so it's become, call it 303 Kelvin. Okay, so you use this Kelvin to put into the equation, and it must be consistent throughout your analysis. Okay, nobody wants to enter. Okay. All right. Using the air standard cycle as well, you can then reduce if you're not given the value of K, but you are given the value of constant specific heat at constant pressure and at constant volume. So you can use the equation to define the value of K. Okay, so this is the arrangement here. Okay, and then expansion from the previous slide, so you can put it as this representation. And then under the cold air standard assumption, the relationship between the initial and final state of the isotopic process can be related using this following equation. And then we use the ideal gas equation of states. So by using this equation, we can then end up having this relationship. And then we expand the previous equation, and then you have a different way to derive the equations. Okay. So when you have a different way to derive the equation, then you can, it depends on what are the values available. Depends on will you be given the value of the volume, or you are given the temperature ratio, or maybe you are given the pressure ratio. So as long as you know which equation to use, depending on the amount of information that you have at hand, then you can select which equation to use. Most of the equations for the thermodynamics too are given in the questions, or I think what happened last semester, what happened is that before you can access, when you click the question that you need to answer on the author platform, there is an additional page which outlines all the related equations for that particular chapter. I think that that was what were given last semester. So you need to be aware. So if it's not given, then unfortunately they need to, I know it's quite challenging to assume that you remember everything, because if we are having face-to-face examinations, usually on the printed questions, we give out all the relevant equation for thermodynamics too, so the student will not need to remember all the equations. But since we are having an online assessment, although I think I've mentioned the needs to the coordinator. So hopefully for this time round, he will upload all the relevant equations for your exam. Okay. So this is the auto cycle, the thermal efficiencies. Can using when we say thermal efficiencies, so just now it's also the same efficiency based on the temperature. So you arrive at the same thermal efficiencies, and then you expand also the temperature ratio based on the volume ratio. Okay, and cycle analysis. Why is it repeating? Sorry about the slide are repeating. So it's also been given just now. There is a condition for using this equation. The over equation is only valid for the ideal auto cycle under the cold air standard assumptions. Okay, so what does it mean? It means that when you answering your exam question, okay, in your answer, you put down the assumption. What is the assumption that you use to answer the questions? Okay, so usually when you have your piece of paper, so you state the number that question that you want to answer. Let's say that you answered question number 5. So what are your assumptions? So 1, 2, 3. So one of the assumption that you need to put in is that you assume that everything is behaving as the cold air standard assumptions. By mentioning this simple statement, you can then use this simplified equation to carry out the auto cycle analysis for spark ignition engine. Okay, and then another good thing is that usually if you are able to write this down, at the minimum you will get around 1 mark at least, because you are telling the examiner, you are telling me that all your calculations carry out based on a valid assumption, a valid engineering assumption. Okay, the thermal efficiency of an ideal cycle depends on the compression ratio and the specific heat ratio of the working fluid. So it depends on R and also value of K. So since you are dealing with X, so you are looking at the properties for N. So this is a basic summary function of this one. This equation I will look for the second the cold air standard assumptions. Okay. So auto cycle analysis, just a reminder to student, is you use this analysis for spark ignition engine. Okay. So do not use it for diesel or compression engines. It's all equal for petrol engines. Okay, so spark ignition, the ideal cycle is the auto cycle. Why you use the auto cycle? Because you assume everything as the cold air standard assumptions. Okay, and then you need to have the PV sketch, the first priority, and then on top of that, ATS sketch. Okay, the next one is the diesel cycle, the ideal cycle for compression ignitions. So compression ignitions. So the difference with the spark ignition, for diesel cycle, the ignitions is because of the high pressure inside the chamber, and then once the pressure reach the required pressure, they can encourage combustions. The fuel will be injected, and then it quickly, before the fuel enter at this level, everything is a liquid. Once it escapes through the tip of the injector, it will become vapor, and then you have everything as vapor. And then the air also exists as a gaseous condition, so both are of the same phase. So you can then create the reactions, and then the fuel simply initiate the combustions. Okay. The difference is that this is the main difference. For spark ignition, you are supplying air and fuel mixtures. But for the diesel engine, what is happening? You only take into the chamber the air. Okay, there's no mixtures. It's only that for the ignition, for the compression ignitions, you using the liquid is injected into the chamber. So please remember or really understand the differences between gasoline engine, or we call it as the spark ignition engines, against the diesel engine, or we call it the compression ignitions. What is supplied for the spark engine? Air fuel mixtures. For the compression ignitions, what is being supplied is the air. And then the piston going up, compress. This one also goes up, compressing it. And then one is reach the TDC, the fuel will be injected, and because everything at the same everything is happening at the same pressure and temperature, so explosion happening here, and then you get the combustion and push the piston downwards. Okay. The combustion process takes place over a longer interval as opposed to the spark ignition process. Combustion process in the ideal cycle is approximated as a constant pressure. Okay. Because injector will inject the diesel fuel once the piston reach the TDC. Okay, and then the pressure is assumed to be constant. So the heat addition process is assumed to happen. It's approximately is assumed to occur approximately as a constant pressure heat addition process. Okay. So if you look back into the PV sketch for spark ignition engine, so the difference is that the two free process. For the compression ignition, state 2 to state 3 is happening at constant pressure. Okay, whereas for the Otto cycle or spark ignition is happening at the constant volume. Okay, so yang ini is step 2 and step 3. Tapi for the diesel is happening at constant pressure. So heat addition is happening at the constant pressure process, and expansion remain the same, and then the rejection of keyword also remain the same. So 1 to 2 is the isotropic compression, and then you have the heat addition at constant pressure, the expansion, the isotropic expansion, and also the constant volume heat rejection process. Petrol and diesel engines differ only in the manner of the heat addition process take place. Okay, petrol at constant volume, diesel engine at constant pressure. Okay, it's approximated as a constant process in petrol engine and constant pressure process in the diesel engine cycle. So that's why you have two different sketches for SI and CI engines. And then using the same approach, you then calculate what will be the heat supply, because diesel, everything happening at the constant pressure, so we use the value of Cp. Whereas for the spark ignition, because everything happening at a constant volume, so we use the value of Cv. But for this one, the amount of energy that we need to calculate is based on the value of Cp. And Q is for this one is delta H, is the enthalpy, which is equal to Cp delta T. Okay, so please identify the differences. However, for the heat rejection still happening at the constant volume. So that's why when you derive the thermal efficiency for the diesel cycle, it is greatly different than the thermal efficiency for the diesel engine. So you can see here, this is a bit longer. Okay, why? Because it involves Cp and Cv. Okay, so each of these carry the same definition as before. R is still the compression ratio. So you derive everything back, and again, reminder, temperature must be in Kelvin. So you derive, so you end up the thermal efficiency. as the following call it expression. Okay, as a cycle, I think this is a repeat on the slide that before. Okay, you can also use the value of the mass using this equation MCP. Okay, delta T, right, same condition. Right. So the next one is if you want to compare between both cycle, because usually when you will be wonder which one will carry the better efficiency. Okay. For the same compression ratio, thermal efficiency of Otto cycle is greater than that of the diesel cycle. Okay. If you are having the same compression ratio, so in terms of thermal efficiencies, Otto cycle is much better. Okay. Uh, However, thermal efficiency of large diesel engines range from 35 to 50%, high efficiency and low cost and diesel. Okay. But in terms of fuel economy, diesel is better than the petrol fuel or the auto cycle. So you can also refer to this comparison where you have the compression ratio as the X exists, and then here is the compression ratio for the auto cycle and the thermal efficiency. So you can see here as the cut-off ratio decrease, the thermal efficiency of the diesel cycle increase. Okay. For similar compression ratio, the efficiency of the auto and diesel cycles are identical. Okay. Sorry, for compression ratio equals to 1, the efficiency of auto and diesel cycle are identical. All right. Okay. The next one is that there is an attempt by scientists and engineers related to fleets and also internal combustion engines, where they want to combine the the virtues of both cycle, okay, as one singular cycle. So it based on that it arrived at the concept of dual cycle. How they are pushing the engines towards this dual cycle is by preparing combustion system which utilize both spark ignition concept and also the compression ignition concept. So this ideal cycle is called the dual cycle. So if you notice here, you look at the dotted line. Okay, this is the auto cycle. This is the first auto cycle, and this is the diesel cycle. So you have the constant pressure process, and this is the constant volume. Now engineers and scientists are working trying to combine both because you want to increase the cross the area under the plots under the graph. So I think the most successful one, I think, coming from the engine from Mazda. Okay, they're still pushing it towards that. Because the challenge of having this dual cycle that you need to use two type of fuel. The one that is compatible for spark emission, and then another type of fuel is you can use at high pressure, which is during the compression ignition cycle. Another name for this dual cycle is also called as the mixed cycle or semi-diesel cycle. And so the characters is you have two stages of a heat addition process. So I think that's it. That's it for the notes. So stop recording. Stop sharing. Let me open up another slide. Okay, just almost similar content, just repeating a bit because there are some content that can assist in understanding. Okay, using this, okay, kind of cycle, right? So a reminder to you, chapter 3 and actually internal combustion engine is chapter 5 in bracket ICE. So these two chapter, and what else? I think chapter 2. Okay, you can use this for the chapter 3. Chapter 2 and chapter 5, the air standard assumptions where we replace, okay, because we know in actual device it has the combustion chamber. Okay, so for the internal combustion engines, you either have the spark plug, okay, or you have the fuel injector for the diesel engine. So you have the diesel injector, and then if you remember the Brayton turbine cycle, based the Brayton cycle for the turbine system, gas turbine, so it also have a combustion chamber. Okay, so to reduce the complexity of visualizing or calculating the amount of fuel actually entering the system, you replace everything by representation of heat being supplied. So you have the Q in parameter, and then you neglect the presence of fuel. So everything you assume air is being supplied into the chamber, and then once the Q in is supplying into the system, is being supplied to the system, and then after that you escape from the given control volume. So this heat addition process is what based on the air standard assumptions. Okay. And then what is the air standard assumption and the cold air standard assumptions is when you consider the working fluids is going to be air, and it has the constant specific heat at room temperature. So these both assumptions must be taken into consideration when you're solving problems related to chapter 5 and also for chapter 2 for the Brayton cycle, chapter 5 for the internal combustion engines. Okay. Air standard assumption, the first one, everything is air. Okay, security and closed loop, and then everything is internally reversible. The combustion process is replaced by heat addition process. So if you for the Otto cycle, you have the constant volume process, everything happening here, and then for the diesel cycle, happening at the constant pressure process. Okay, and lastly, the exhaust process is replaced by the heat rejection process, which is the Q out. Q out here, and you have the Q out there, bottom. And then you can refer to the value of CP. So air standard cycle, following on these two definitions, air standard cycle then can be defined as a cycle for which the air standard assumptions are applicable. So this is where Otto and diesel are valid based on this assumption. Okay. So we've gone through the minimum MEP, the the mean effective pressure. Okay, so this is the arrangement for the piston. So usually we start by the intake stroke, and then we compress, and then you have a power stroke, and then the exhaust. So you notice here the movement of the pistons. Okay, compression stroke, you go up to the top and center, and then you have the ignitions going downwards. Okay, and the piston, once it reaches at the BDC, it goes up again. During the journey moving up, the piston push out the byproduct of combustion through the exhaust port. Okay, and then once it reaches the TDC, it needs to go down again, and then start to encourage the air to enter again. Okay, so these are the four stroke representations. Okay, and we seen just now the equation in the notes by Associate Professor Dr. Nur Shikin. And then this is cycle. Okay, here is just again to remind the students, okay, how the sketch for PV diagram for both cycles is deferred. Is only on this where you have the queue in event is happening. Okay, and then this is the TS diagram. Okay, so basically those are the things that is you need to take into account for this chapter. Start. Start recording. Let me open a few example of questions. All right, sorry again. Okay, this example of the previous two semesters questions, 2019. Okay. The question asks you to differentiate between auto and diesel dual cycle. So the best way to answer this is to sketch the PV cycle for both system. So example here. Okay, you sketch the auto cycle and the dual cycle, the PV diagram, and then you indicate where the heat addition process is happening. It must be at process 2 to 3 for the auto cycle, and for the dual cycle, you know, as the name suggests, it has two heat addition process, 2 to 3 and then 3 to 4 caches. And then the second part of the question is asking based on a diesel cycle problem. It has the compression ratio, the caloric ratio, and then you know and then the question give out the amount of power the cycle produce, and then the conditions before the compression is happening, and then the temperature, and then it's also hint that you can use the constant specific heats at room temperature. So which means that you can adopt the air standard assumption, and also the air standard cycle, and also the cold air standard assumption. Okay, so this is the not to worry about the answer scheme, because call it it's actually taken from the Chengel and Bull's book. For a certain semester, the question is a bit different compared to this kind of question, because a certain stage you need to think beyond the cycle type of questions. Okay, so in here you sketch the PV diagram for the cycle, and then you use the equation that I mentioned. If the equation, I think student may have some challenges in remembering this expression. Okay, like I mentioned just now, if we are having a face-to-face examination, all the equation, this one, and this one will be included on the exam paper, and then student can just refer to it. Okay, like this example here, you can see here that all the equation related to the problems and the exam are included. But this is for the face-to-face examination. But for the this cutoff ratio, RC, the ratio between P3 over P2. But for the online exam, you may not have this kind of list. Okay, so should you prepare? Yes, I think you can prepare the list of equation that you're going to use for answering the exam. Okay, so that it's easy for you to solve the problems. Okay. And then using the equations, and then you solve the problems. In here, please, if you look at the question, it doesn't ask you to do the PV sketch. Even though it doesn't ask you to sketch a PV diagram, but it's best that you always sketch the PV diagram. Okay, and a note to the students: when you answer thermodynamic question, I think it's best that you try to use this kind of approach. Okay. Where you no need for you to rewrite the question again, but you jot down or you indicate the main parameters, and then always write your assumptions at the top of your answer script. For example, in here, because using the information given by the questions, you can simply state 3 assumptions. The first one is that everything is following the air standard assumptions, and then you can neglect the kinetic and potential energies. And then thirdly, you are using the ideal gas equation of states with specific heats values. So these are the assumptions. Just put this down on your answer script, and then you will get at least 1 mark. You do this kind of PV sketch, although the question did not ask you to do a sketch, but if you provide this PV sketch, you can get at least 3 marks. Okay. You recall or indicate on your answer script from where you got the main parameters, the value for your main parameter. For example, here the CP, from where you got it, from table A to A. You state on the answer script, you can get another 2 marks here, at least 1 or 2 marks here. So in total, you have 1, 1, 2, and then you have here 2. I think if you do this kind of sketch, I can give you 3. So 1 plus 1, 2, 2 plus 3 is 5. So easily you can get 5 marks by having to indicate the assumption, stating out from where you got the important parameters, by sketching the PV diagram, and also indicating the position of the incoming heat to the system, and also how the system is rejecting the heat. And then you start to put down your expression or formula that you want to use to solve the problem. Okay. So if this one, 1, 1, 2, and 1, 3, so it's already 5 marks. So you have another 10 marks. Okay. So if this one, how many marks here? 16. So 5, so you have another 11. So 1, 2, 3, 4 is about 3, and then another 3. This one 4. Yes, around, maybe it's a bit less. Okay, so this is how the marking scheme is divided. So that's why it's important that you, in most cases, somehow students are not keen to write this. Okay, ramai yang tak tulis dan tak sketch. Sebabnya dia kata sebab tak diminta pun dalam soalan, it's not being asked more. Because when you didn't put anything, didn't put down the assumption, then there's no mark that I can give. You did not sketch anything, then I cannot give you a mark on the sketch and so on. So that's why you need to try to attempt to make extra or to provide extra info for your answer script. Okay, so this is an example of a question that you're going to face for chapter 6 or chapter 5. Okay, so this one example here. Let me see if I have another example. Okay, another example of questions. This one in 2017-18. Slightly longer questions. Okay. In here, the question asks you to differentiate the spark ignitions. So not to differentiate, to explain what are the processes that are involved in spark ignition engines. And then you need to clarify your answer by showing and referring to the engine's indicator diagram. So this is referring to the PV diagram. And then part B, you are given a diesel engine with the volume and then how many cylinders are there, and then the cut-off ratio, compression ratio, and so on. And then you need to determine the temperature at the end of the expansion stroke, and then you need to determine how much power you will deliver in kilowatt if it's running at 3,500 RPM. Yeah, I think it's one parameter that you need to know on top of that. I will put that in the Padlet because I'm not sure for this semester you have question relating to the speed or not, because it's a bit off the syllabus. Okay, so not to worry. So yeah, so this is another example of the exam question that you're going to face. It's only that for this question 6 part B part 2, the second part here is will require you to use different kind of formula. Let's see, does it provide? No. During this time, it's still not a culture to include equations in the questions. It's only that in 2019 and later that I'm able to persuade the coordinator to include equations. All right, so stop sharing. Let me see if there's anything else to show. By the way, only 60 of you registered your attendance today, so could I have the remaining students, the remaining 2 students to register your attendance? Okay, test 1 marks. Test 1 marks. Oh yeah, test 1 marks. All right. Already finished marking the test 1. I will. What happened? Okay. Shall I put the marks on the classroom? Is that okay? So.
Okay, Doctor.
All right. I think only one of you did not make it. Did not pass the test 1, and then maybe one or two got a bit lower than others. So I will try to contact one by one for those who are having some low marks and so on. Okay, so I think that's all for today. Yep. Any question?
Can I ask about the group project?
Yes.
Uh, we still can't imagine about the diagram and the calculations of the project. We don't know how to design it actually.
Um, okay. I think last time I already explained, right?
Yeah, but we still can't imagine how it works. And the calculations also are still it's like a problem.
Okay, the calculation is what you need to carry out because that is where the student need to do the analysis. I think yeah, I can explain again. Mm, Let me let me prepare something. Okay. For others who want to exit, it's okay as long as you record your attendance in case you have a different. I mean, you have challenges to maintain connection. Okay, yang lain kalau nak exit boleh, tak masalah. Pastikan dah isi kedatangan. Okay, hopefully you can see here. You refer to the project brief. So number 3 there. So you need to determine how much water is you going to produce. What will be the amount of water amount that you want to produce. Okay. The project requires you to produce between 15 to 20. So you select one amount. So 20 liter per day. Okay, so what is your selected amount? Okay, let's say that you select 15. And then you need to decide. If you select 15 liter per day, okay, you want your machine to operate for how long? For one day? You want it to operate 24 hours? Or 12 hours? Or 10 hours? Or maybe you want to be like a very limited time, 1 hour per day. So let's say that you are requiring your machine to work for 10 hours per day. So it means that for 1 hour, how much water the machine need to produce? So it's 15 divided by 10, which is 1.5 liter per hour. So this is your output capacity, the required capacity. Okay, so this is the amount that you need to produce. Okay, the next thing is that you are instructed to use the refrigeration system to extract the moistures from the surrounding. So you already finished the chapter on mixture. So you know the influence from relative humidity and specific humidity. And then you know that this project is located uh, on planet Earth. Okay, it's not in Mars or in different planets. So it's in something. I mean, it's close to where we live. So you need to decide: are you going to design your system for usage? I don't know, because you know the Earth is like this. So you have the equatorial line, and then you have the northern hemisphere, and then you have the southern hemisphere, and then you know the value of humidities. Okay. For any regions in the world, they have different humidities values and ratio, and then they have different temperature values. So by knowing this, that you know which region has the most amount of water in the surrounding, and then you are using the refrigeration system. So what is the best system to produce this water. It's not that you're going to produce the water from uh, like you squeezing the lemon, or you want to squeeze out the water from the tree or whatever. You try to extract the water from the environment. If you are trying to extract the water from the environment, that's why in the chapter on mixtures, we have the dew point temperature concept. Okay, and then you have the refrigeration, and then you have the dew point. So you want to push the air to reach the dew point temperature, and then once it reaches the dew point temperature, so you have to configure how you're going to achieve dew point temperature at certain stage of the air flow rate, because you are going to your feedstock, your feed, your input to the system is the surrounding air. The surrounding air is your input, and the air that you push into the system has its own moistures. So the question on how you're going to extract moisture from the surrounding using the dew point temperature concept, and how are you going to control the temperature of the incoming of the air that you are analyzing, is by cooling it down. How? Using the refrigeration system. So how are you going to put the refrigerants? Is it going to what? You're going to surface call it the heat transfer at the surface, or is it going to blow out the cool air, or you're going to how are you going to cool down the air? How are you going to achieve this dew point temperature? And then how once you achieve the dew point temperature, of course the moisture will start to collect. So the moistures will start to appear on the surface of the cool surface, right? And then you need to collect this, but the amount must be 1.5 liter per hour. So what will be the size? What will be the flow rate? What will be the dimension? So that are the tasks that you need to complete.
Doktor, air tu dia akan form dekat evaporator kan?
That's why you need to work out, because I mean, if I keep telling you, then what's the purpose of you constructing the project? Already give out the hints. So how are you going to collect the water vapor from the surrounding?
Okay, doktor. Mixture punya notes tu dekat chapter refrigeration sebab
Mixtures
dekat
punya note dekat
Google Classroom tak ada.
dia ada dia punya sendiri, ada palette sendiri.
Oh, sebab saya cari dekat Google Classroom dia tak ada.
Kalau tak ada, saya I think saya dah bagi. Kalau tak ada, saya minta balik.